No one expected the first alert to arrive the way it did, quiet, almost understated, hidden inside a routine preprint from Harvard's astronomy department. Yet, in just a few sentences, Avi Loeb triggered the most controversial debate in modern astrophysics. His new analysis didn't merely suggest that the interstellar object known as 3I Atlas was behaving strangely. It argued that the comet might have catastrophically exploded into at least 16 symmetrical fragments at perihelion, unleashing a cosmic firework display across the inner solar system. And the shocking part wasn't the claim itself, it was the data behind it, measurable, traceable, and impossible to ignore. The implication was staggering. Humanity was not simply watching a comet pass through. We were witnessing an interstellar object disintegrate in real time, an event so rare that it bordered on impossible. But this was only the beginning, because the deeper the observations went, the more the official narrative began to unravel. The story of 3I Atlas did not start with an explosion. It began quietly on July 1, when the Atlas Survey Telescope in Chile captured the faint signature of an object unlike any previously recorded. Its trajectory was hyperbolic, its inbound velocity abnormally high, its orbital path unmistakably interstellar. In that moment, humanity welcomed only its third visitor from outside the solar system, after Oumuamua in 2017 and Borisov in 2019. But unlike those earlier objects, this one arrived wrapped in strangeness from the start. The designation 3I wasn't just a classification. It became a symbol for an unanswered question about life and intelligence in the universe. The odds of detecting even a single interstellar object in a human lifetime are infinitesimal. Yet here we were, watching a third one streak across the void in less than a decade. And this time, something felt fundamentally different. By late August 2025, the James Webb Space Telescope had locked onto the object with its infrared instruments, revealing an enormous cloud of carbon dioxide surrounding the nucleus, hundreds of thousands of kilometers wide. That alone was unusual, but not unprecedented. What came next was unprecedented. JWST's spectroscopic analysis revealed a chemical fingerprint that did not match any known cometary body. The iron-to-nickel ratio was wildly disproportionate, far outside the range of typical cometary formation, and the organic compounds detected in the surrounding gas cloud refused to fit into any established chemical model. Astronomers initially tried to force the new data into familiar categories, but 3I Atlas resisted every attempt. Its spectral lines were wrong. Its mass loss rate was escalating too quickly. Its coma was too large for its estimated core size. And yet, none of these early anomalies compared to what happened as the object approached the sunday. Instead of slowing down as gravity dictated, 3I Atlas began to accelerate. Not marginally, not slightly, dramatically. Observatories across the world confirmed the same numbers. The object's non-gravitational acceleration climbed to levels never before recorded in cometary physics. At perihelion, astronomers observed an acceleration rate of 94 kilometers per day squared, a figure that simply did not fit into any natural comet model. And it wasn't just the motion that changed. Shortly before its closest approach to the sun, 3I Atlas began to turn blue. Typical comets glow white, yellow, or slightly greenish as dust, and common molecules reflect sunlight. But Atlas began emitting spectral signatures associated with ionized cobalt, titanium, and rare interstellar metals. These were materials almost never seen in active jets of comets. The standard explanation was immediate: extreme outgassing. Powerful solar radiation was vaporizing volatile elements and ejecting them into space. But within days, the numbers proved the explanation couldn't hold. From early August to late October, the mass loss rate of 3I Atlas surged from a modest few hundred kilograms per second to nearly 2 million kilograms per second, an increase so extreme that it resembled 2 skyscrapers being vaporized every single second. No known comet could survive that rate of material loss without breaking apart instantly. Yet 3I Atlas did not disintegrate at perihelion, at least not visibly. Then came the shock wave in the scientific community. In early November, Avi Loeb published an analysis that confronted the paradox head-on. The energy radiating from Atlas did not correspond to the amount of mass it was shedding. Something else was contributing to the energy output, something that was not accounted for in standard comet models. The numbers simply refused to balance. And so, naturally, the questions began. Some scientists proposed a possibility that would have been dismissed as absurd only a few years earlier. What if 3I Atlas was not a natural body? What if, triggered by the extreme heat of the sun, it had activated like an ancient probe drifting through the galaxy for millions of years? What if the blue light was not simple ionized dust, but a sign of an artificial energy system coming online? The speculation wasn't proof. It wasn't even consensus, but it became impossible to ignore after the next observation. Just days after perihelion, the signals coming from the object suddenly vanished from JWST's view. What remained was a faint, impossibly long ribbon of scattered light stretching millions of kilometers and no detectable core. At the same time, solar flux data showed that at perihelion, 3I Atlas absorbed roughly 700 joules of solar energy per square meter per second. For a natural comet to produce the observed mass loss under that level of heating, its nucleus would need to be enormous, on the order of 140 kilometers. But Hubble's July images had already confirmed the core was only about 2 kilometers wide. The math did not leave room for ambiguity. The object was too small to lose that much mass, too energetic to match sublimation physics, too stable for the forces acting on it. And yet, it behaved as though it had multiplied its surface area by a factor of 16. Which is when Loeb presented the only explanation consistent with the numbers. The nucleus must have fragmented into at least 16 pieces during perihelion, each increasing the effective area absorbing solar radiation. A catastrophic breakup. Mathematics never lies, but mathematics can reveal truths we are not prepared to confront. By November 10, Loeb's findings were public. The astrophysics community erupted. Observatories scrambled for follow-up observations. Debates exploded across universities. Yet, even in the chaos, one sentence from Loeb stood out calm, quiet, and colder than anything else. This process may not be entirely natural. And just like that, the question changed. It was no longer simply, what happened to 3I Atlas? It became, what exactly are we dealing with? If the story had ended with a simple fragmentation event, the explanation might have satisfied most astronomers. Comets break apart, nuclei crack under thermal stress. Solar radiation destabilizes fragile structures. But the aftermath of 3I Atlas did not resemble any known breakup. In fact, the more closely scientists looked, the more obvious it became that the expected debris field wasn't behaving like debris at all. When a comet shatters, the pieces expand outward chaotically, carried by solar wind into a widening plume. Yet, in the days after perihelion, the region around 3I Atlas displayed something else: patterns, structures. Organized strands of material behaving as if guided by forces beyond random physics. And the first people to see it weren't major space agencies, but two British observers armed with advanced imaging software and a telescope that should not have been capable of changing the course of the conversation. On November 9, Michael Boutner and Frank Knobling of the British Astronomical Association captured a set of images that rearranged the debate. What they found was not a diffuse cloud spreading like smoke after an explosion. Instead, it was a system of luminous streams pointing in specific, impossible directions. The most startling was a bright structure known as an anti-tail, a beam of light pointing directly toward the sunday. Comet tails are pushed away from the sun by radiation pressure. They never point inward. An anti-tail only forms under rare geometric alignments, or when a physical mechanism forces material against the direction of solar wind. Here, the geometry didn't support that scenario. Something else was directing the flow. And then came the second shock. Boutner and Knobling found not one anti-tail, but multiple narrow jets, two of which pointed exactly toward the sun, extending almost 1 billion kilometers into space. One central jet stretched more than 280 million kilometers, nearly twice the distance between Earth and the Moon. But it wasn't their size that caused alarm. It was their precision. These jets were clustered, aligned, and sharply defined, like the exhaust of a propulsion system, instead of the chaotic spray of sublimating ice. Within 24 hours, additional images appeared from astrophotographers across Europe. Martin Jaeger, G. Raman, E. Prosper, each capturing the same disturbing symmetry. At least 7 distinct jets radiated from the remnants of 3I Atlas, forming geometric patterns that pointed to consistent coordinates on the ecliptic plane. Their angles weren't random. Their spacing followed a repeated sequence. They looked intentional. Not everyone accepted that interpretation, but the data spoke for itself. Jets from natural comets fluctuate, bend, and twist as they interact with solar, wind, and microrotations of the nucleus. The jets from Atlas didn't flicker, they didn't warp. They held formation as if locked in place. Some scientists compared the configuration to a network of directed energy beams. Others suggested that the geometry could be the footprint of an ancient mechanical structure now reacting to extreme solar heating. The mainstream community hesitated to theorize so boldly, but very few could explain why the jets fired at regular intervals, or why they remained strikingly coherent after the supposed fragmentation. If the core had shattered into 16 independent pieces, why did the outflow behave as if a single, unified system still existed? This was the moment when public curiosity turned into geopolitical interest. NASA's silence became conspicuous. The European Space Agency expanded its observation schedule without explanation. China and Russia redeployed high-orbit tracking assets, while leaked orbital data hinted that 3 military reconnaissance satellites had quietly shifted their positions to monitor the region around Atlas. Analysts began to suspect that the object's trajectory after perihelion was causing alarm. One of the major jets, one that Loeb had estimated could be contributing to non-gravitational acceleration, appeared to be altering the motion of at least one fragment in a direction tending toward Earth's orbital path. The deviation was small, but real. It suggested control, whether intentional or incidental. The adjustment raised questions that no government was prepared to answer publicly. By mid-November, radar facilities in the United States and Europe began detecting something even stranger: pulsed reflections. Instead of a simple, steady echo from tumbling debris, the radar return oscillated in repeating intervals. Some analysts wondered whether the pulses were caused by a rotating, reflective structure. Others asked a more unsettling question: what if the pulses were being transmitted not reflected. No agency confirmed anything. No agency denied it either. Meanwhile, Avi Loeb continued following the data trail. He examined the new images and compared them with his earlier calculations. According to his estimates, the mass loss rate had soared to nearly 50 billion tons per month. Yet, if Atlas truly had fragmented into 16 pieces, each individual nucleus should have been too small to sustain such extreme outgassing. A natural fragment of that size could not maintain the power output observed. It would evaporate far too quickly. The paradox deepened. The fragments were too small to lose so much mass, but the system was too coordinated to be random. Something was driving the jets, maintaining symmetry and producing a structure that defied the concept of a cometary breakup. Mainstream astronomers rushed to reinforce more conservative explanations. They compared Atlas to comets like 73P, Schwarzmann-Wachmann, which shattered repeatedly in 2006, or Neowise, which displayed unpredictable jets. Thermal stress can rupture nuclei. Internal pressure can build until an object splits, like cracking ice. Sublimation can accelerate abruptly, especially near perihelion. But in every model they produced, inconsistencies multiplied. Internal temperature thresholds didn't match the observed timing. The fragmentation should have been more chaotic. The sublimation rate should have tapered more gradually, rather than spiking exponentially. Above all, nothing in standard comet physics generates symmetrical jets pointing exactly toward the sunday. That was the detail no one could account for. It was in this vacuum of explanation that Loeb presented his most controversial argument. If the natural physical models failed to explain the data, he said, then we must consider alternative frameworks. His proposal was not sensational, nor was it framed as a claim. He simply asked whether the jets could be the result of active propulsion. He pointed out that advanced thrusters could generate far greater exhaust velocities than natural sublimation processes. With much smaller mass loss, such thrusters could produce the observed accelerations and maintain jet coherence. The geometry of the jets matched what one might expect from a directional propulsion array. He never said the word alien. He didn't need to. The scientific implications alone were enough to shake the field. If Atlas was a natural comet, it would soon become obvious. The fragments would continue drifting apart. The jets would lose coherence. The mass loss rate would collapse. But if the nucleus remained structurally intact and the jets kept firing in organized directions, the truth would be impossible to ignore. And with the object's closest approach to Earth looming on December 19, time was running out. Observatories prepared for the decisive campaign. Hubble scheduled ultraviolet spectroscopic measurements for late November. James Webb prepared to observe the post-perihelion phase in December, equipped to capture the chemical signatures and structural details that would reveal whether Atlas was a shattered comet or something unprecedented drifting through the inner solar system. Whatever the answer would be, the next observations promised clarity. Or perhaps they promised something far more unsettling. The weeks following the first wave of post-perihelion observations transformed the mystery of 3I Atlas from a scientific curiosity into something larger, something that stretched the limits of astronomy, physics, and humanity's sense of its place in the universe. Every new fragment of data raised more questions than it answered. Every silence from space agencies only deepened suspicion. And every passing day brought the object closer to its brief encounter with Earth, the one chance for clarity before it vanished forever into the cold dark between the stars. For astronomers, the timeline had suddenly become brutally tight. December 19, Atlas's closest approach was etched into every research schedule across NASA, ESA, JAXA, and the global amateur network. Hubble's ultraviolet spectroscopic campaign in late November promised to reveal the elemental ratios in the jets. James Webb's December observations would measure the thermal signature of the supposed fragments. If the object had truly broken into 16 pieces, the infrared cameras would see the cold voids between them, the separate nuclei radiating independently. If not, if the structure remained coherent, then all previous assumptions would collapse. The implications of these observations reach far beyond cosmic archaeology. They touched on deeper questions. What kinds of objects travel between stars? Are they remnants of ancient systems, natural wanderers, or relics of something engineered long before humanity evolved? Yet, as November unfolded, the picture refused to settle. Radar returns showed the same rhythmic behavior pulses repeating like a low-frequency signature. Astronomers attempted to model the origin, but none of the simulations matched the exact regularity. Some argued it was an internal rotational modulation. Others believed the pulses indicated a structural resonance, perhaps a periodic heating cycle. A minority whispered a third possibility: intentional signaling. Meanwhile, the comparison with previous interstellar visitors cast Atlas in an even stranger light. Oumuamua, silent and inert, had accelerated slightly through non-gravitational forces that remain debated even today. But it produced no jets, no tail, no energy outbursts. Borisov, on the other hand, behaved like a textbook comet, volatile, active, yet fully explainable. Atlas existed between these extremes. It displayed cometary chemistry, yes, but everything else, its mass loss rate, its acceleration, its jets, its fragmentation, broke the pattern. No natural explanation encompassed all the anomalies at once, and patterns, once noticed, are impossible to unsee. Researchers began noting the interconnected nature of Atlas's behavior: the anti-tail formation, the precise jet alignment, the unprecedented shift into the blue spectrum, the symmetrical fragmentation pattern Loeb proposed, the acceleration spike, the vanishing of the nucleus from JWST's field of view, the pulsating radar echoes, the coordinated trajectories of the suspected fragments. Individually, each anomaly might be explained away. Together, they formed a mosaic that looked less like chaos and more like intention. But science does not declare intention without proof, and the window for proof was closing. Rumors spread about ESA's internal disputes. Some teams pushed for full public release of Mars Express's solar conjunction images, which may have captured the object's structure at its most active phase. Others insisted the data needed to be reviewed carefully before publication. The phrase became code for something else, something sensitive enough to delay disclosure. At the same time, independent observatories detected small but periodic alterations in Atlas's motion adjustments that resembled active navigation. Nothing dramatic. Nothing that would alarm the general public. But to those who studied orbital dynamics, the pattern was unmistakable. A sequence of tiny course changes, spaced across days, as though the object was responding to the sun, to radiation pressure, or perhaps to something else entirely. As these observations accumulated, the tone of the debate shifted. What had begun as a geological argument about comet physics evolved into a philosophical confrontation. If Atlas was natural, it would eventually reveal itself as such. The fragments would separate, the jets would decline, the anomalies would flatten into noise. But if the object remained unified, if the jets continued firing in geometric patterns, if the blue spectrum intensified, if the acceleration persisted, if the radar pulses remained regular, then astronomers would be forced to question assumptions held for generations. And the world braced itself because there was no precedent for an interstellar object performing controlled maneuvers through the inner solar system. Humanity's observing networks prepared for the decisive days. When Atlas reemerged from solar conjunction on November 11, telescopes across the globe locked onto its new position. For the first time in history, an interstellar visitor would be tracked continuously from inside the solar system through perihelion and all the way toward its outbound trajectory. The data influx became overwhelming terabytes poured in from instruments on Earth, from space telescopes, and from the amateur astronomy network, whose contributions rivaled those of major observatories. Each data set added another piece to the puzzle, but none assembled the full picture. The fragments, if they were fragments, remained too close together to resolve cleanly. The jets appeared as bright lines cutting through the darkness. The blue glow persisted. In scientific conferences, debates raged with an intensity rarely seen. Was Atlas exhibiting exotic sublimation physics? Was it an artificially fragmented comet designed to maximize surface area? Was it a relic of a dead civilization? Was it simply a statistical outlier, a once-in-a-million object that would reshape our theories without requiring technological explanations? No one could say for certain, but one truth united every side. The next 6 weeks would decide everything. If the Hubble and Webb images revealed multiple independent nuclei, the story would settle into the domain of natural phenomena. A remarkable comet, a violent fragmentation event, a spectacular but understandable display of cosmic mechanics. But if the nucleus appeared intact, if it still functioned as a coherent body producing aligned jets, then the universe would suddenly look far less empty than we believed. In quiet corners of observatories, scientists acknowledge what they rarely admitted publicly. Humanity may be experiencing the first direct encounter with a messenger from beyond. Not metaphorically, not philosophically, but physically. An object bearing information in its structure, its chemistry, its behavior. What troubled them most was the timeline. After December 19, Atlas would begin drifting toward Jupiter's orbital region, then fade beyond observational range by January. By spring, it would vanish into the black ocean between stars, never to return. The data collected in these few fleeting weeks would be the only record future generations would have. A moment of coincidence so improbable, it bordered on cosmic choreography. And that thought lingered in every discussion, every meeting, every late-night data review. Why now? Why this year, this alignment, this moment when humanity had just enough technology to observe, but not enough to reach? Was it chance? Was it fate? Or was it simply the indifferent mathematics of celestial motion? As the days marched forward and the debates intensified, one truth crystallized. Whatever Atlas was natural or engineered, ancient or newly awakened, inert or active, it had become part of humanity's story. Not as a threat, not necessarily as a harbinger, but as a reminder that the universe is far stranger, far richer, and far more unpredictable than our models suggest. The jets were real. The acceleration was measured. The debris, if debris existed, defied every expectation. Somewhere in those spectral lines, in those pulses, in those images, lay an answer that would reshape our understanding of what moves through the interstellar medium. The window was closing, and humanity had one chance to listen.